This mini lecture discusses how to balance redox reactions. This topic is usually included in the introduction to redox reactions, like in chapter 8, but for some reason this textbook saves balancing for later, including it as the first part of a chapter on electrochemistry, which is a topic that'll be covered later in Chem 122. So, we're going to just dip our toes into chapter 19 so that we can wrap up this discussion of reaction types from chapter 8. As noted in the last lecture, balancing a redox reaction involves considering not only the number of atoms on both sides of the reaction, but also the number of electrons being transferred, as the number of electrons lost by one chemical species needs to match the number of electrons gained by another chemical species. This can be extremely difficult and sometimes impossible to do by just looking at the reaction itself. So a specific sequence of steps is used to ensure that we are considering all aspects of the balancing process. The first steps in this process were introduced in the last mini lecture, with the reaction shown above, and involved assigning oxidation states to all atoms in the reaction and determining which atoms are being oxidized and reduced by noting the changes in the oxidation state. We can tell that this reaction is not balanced for charge because the total charge on the reactant side and product side of the unbalanced reaction do not match. Note that the neutral copper and silver 1 ion on the reactant side add up to a total charge of positive 1, whereas the copper 2 ion and neutral silver on the product side add up to a total charge of positive 2. So the reaction is not balanced for charge. After identifying what is being oxidized and what is being reduced, the half reactions for the oxidation and reduction are written separately, with electrons used as products or reactants in each half reaction. Note that the half reactions, if written correctly, should be balanced for charge even if the overall reaction is not yet balanced. In the copper oxidation, the reactant side has a charge of 0 because the neutral copper atom has a neutral charge. And the product side also has a total charge of 0, as the positive 2 charge on the copper cation cancels out with the negative 2 charge provided by the 2 electrons. In the silver reduction reaction, the reactant side has a total charge of 0 as the positive 1 charge on the silver cation cancels out with the negative 1 charge of the electron, and this matches the product side that has a neutral silver atom with 0 charge. Again, we can see from the half reactions that the number of electrons does not match. There are 2 electrons being produced by the 1 copper atom, but only one of those electrons can be gained by the 1 silver ion. So since we can't have a leftover electron floating around, we need 2 silver ions so that both of the electrons lost by the copper have somewhere to go. By multiplying the silver reduction half reaction by 2 and then combining both half reactions, the final balanced overall reaction is determined. When combining the 2 half reactions, anything that is the same on the reactants and product side cancels out. So the electrons cancel out, which is why they aren't included in the overall balanced reaction. This is similar to how spectator ions that are the same on both the reactants and product side in precipitation reactions can be canceled out in order to determine the final net ionic equation for the reaction. Finally, we can double check that the reaction is now balanced by adding up the charge on both sides of the balanced reaction and making sure it matches. The neutral copper and 2 silver cations add up to a positive 2 charge on the reactant side, as does the copper 2 plus cation and 2 neutral silver atoms on the product side. Note that the total charge simply needs to match on both sides. It does not need to equal 0 or be neutral overall. It simply needs to match. Where the half reaction method really makes sense is with more complicated redox reactions that take place under basic or acidic conditions, where the solvent, water, and the ions that water is composed of, H plus or hydrogen ion and OH minus or hydroxide ion, are involved in the reaction. Over the next few slides, we'll look at how to balance reactions in acidic solution and then see one extra step that allows for balancing in basic solution. We start by determining the oxidation states of the provided reaction. Copper sulfide is an ionic compound where the copper has a positive 2 charge and the sulfur has a negative 2 charge, so the charge indicates the oxidation states. For the polyatomic ion nitrate, each oxygen has a negative 2 oxidation state, as indicated here. So if there are 3 oxygens and an overall charge of -1 on the ion, then the nitrogen must have an oxidation state of +5 in order for the sum of all the oxidation states of each atom to equal the overall charge on the ion. If this is unclear to you, feel free to pause the lecture and think about this a little bit more. On the product side, the copper-2 ion just has an oxidation state that matches the +2 charge. The sulfate polyatomic ion is solved similarly to the nitrate ion, with oxygen again having a -2 oxidation state based on the rules that we assume for oxygen. And with 4 oxygens and an overall -2 charge, this means sulfur has to have an oxidation state of +6, so that the sum of all the oxidation states for each atom in the sulfate ion add up to the overall charge of -2 on the ion. Again, if this is unclear, pause the lecture and see if you can sort this out by thinking through it a little bit more. Finally, the nitrogen monoxide has another oxygen with an assumed -2 oxidation state. So that means the nitrogen must have a +2 oxidation state, since this entire molecule is neutral and therefore the oxidation states should cancel out. Once the oxidation states are determined, we see that sulfur and nitrogen are the atoms whose oxidation states are changing in the reaction, with the sulfur being oxidized because it is losing electrons to go from a -2 oxidation state to a more +6 oxidation state. And so that's a total of 8 electrons that are being lost. So writing down all the chemical species involved in the oxidation reaction, the copper sulfide will be on the reactant side, and then the copper-2+ ion and sulfate ion will be on the product side. Note that any atoms that are included in the reactant that is being oxidized, so the copper sulfide, need to be represented on the product side as well. And so this is why the copper-2 ion is included on the product side, even though it doesn't contain the sulfur atom that is undergoing oxidation. The nitrogen up above is being reduced in this reaction because it is gaining electrons to go from a +5 oxidation state to a less positive or more negative oxidation state of +2, which means that it has gained 3 electrons. So, writing down all the chemical species involved in the reduction reaction, the nitrate ion is on the reactant side and the nitrogen monoxide is on the product side. And those are the only chemical species that are needed to account for all atoms in the reactant, nitrate, that is being reduced. Finally, note that the oxidation states of the oxygen and copper do not change in this reaction, and it will often be the case that several atoms retain their same oxidation states when we have more complex redox reactions like this one with a lot of atoms that are involved. Next, we must balance the half reactions, as currently the oxidation half reaction is balanced for electrons, but it's not balanced for atoms, as we don't have any oxygen atoms on the reactant side. The reduction reaction is also unbalanced in both atoms and charge. The steps for balancing these half reactions involve a very specific sequence. First, we balance any atoms that are not oxygen or hydrogen. In this reaction, that would be the copper, sulfur, and nitrogen. Luckily, we see that these atoms are already balanced in both half reactions, so we don't need to do anything. However, do not forget this first step, as it is a crucial step for some reactions. Next, balance the oxygens by adding water to the opposite side. So in the oxidation reaction, 4 water molecules are added to the reactant side to balance the 4 oxygens on the product side. And in the reduction reaction, 2 water molecules are added to the product side to balance the 3 oxygens on the reactant side. By adding water, hydrogen is introduced into each reaction. So it is crucial to balance oxygen before balancing hydrogen, as adding water always changes the number of hydrogens in the reaction. When balancing hydrogen, add hydrogen ions, or H+, to the opposite side. So for the oxidation reaction, 8 hydrogen ions are added to the product side to balance the 8 hydrogen atoms in the water molecules on the reactant side. In the reduction reaction, 4 hydrogen ions are added to the reactant side to balance the 4 hydrogen atoms in the water molecules on the product side. It is crucial to balance hydrogen before balancing the charge, as the hydrogen ion introduces positive charges and changes the total charge on that side of the reaction. To balance the charge, or the electrons, determine the total charge on both sides of the reaction and then add electrons to the side with the higher positive charge in order to decrease the charge to match the side with the lower charge. In the oxidation reaction, the reactant side has a total charge of 0, and the product side has a total charge of positive 8. So, 8 electrons are added to the product side to decrease the total charge from positive 8 to 0 so that it matches the charge of 0 on the reactant side. In the reduction half reaction, the reactant side has a total charge of positive 3, and the product side has a total charge of 0. So, 3 electrons are added to the reactant side to decrease the total charge from positive 3 to 0 to match the product side. Again, it is not the goal to make the charge equal 0 on both sides in every reaction. It is simply the goal to make the total charge on each side match. Sometimes the matching total charge may be a positive value, and sometimes it may be a negative value, or sometimes it may be 0, as in this case. Note that the number of electrons in each half reaction matches the change in oxidation state for the element being oxidized or reduced in that half reaction. This is a good way to double check that your balancing makes sense. Another thing to check is that the oxidation reaction should have electrons on the product side, whereas the reduction reaction should have electrons on the reactant side, as these are the rules that these half reactions always follow. Note that the presence of the hydrogen ions in these half reactions indicates that the reactions are happening in acidic solution, where an excess of hydrogen ions would be available. But we can also balance the reaction in basic solution, and I'll show this in a few slides. Now that the half reactions are balanced, we can see that the number of electrons in each half reaction does not match. To fix this, we find a least common multiple between 3 and 8, and use it to determine what factor to multiply each half reaction by. The least common multiple between 3 and 8 is 24, so the oxidation reaction is multiplied by 3 to give 24 electrons, and the reduction half reaction is multiplied by 8 to give 24 electrons. Next, add the two half reactions together and look for things that cancel out on both sides. The first thing that should cancel out is the electrons, as that is the main goal in the half reaction method, to balance and therefore cancel out the electrons in the half reactions. Next, notice that there are now water molecules on both sides. So all 12 of the water molecules on the reactant side cancel out with 12 of the 16 water molecules on the product side, leaving 4 water molecules. There are also hydrogen ions on both sides. So 24 hydrogen ions cancel out on the product side with 24 of the 32 hydrogen ions on the reactant side, leaving 8 hydrogen ions. So the final balanced reaction in acidic solution is now determined. And at this point, it is a good idea to double check that the number of atoms of each type match on both sides, as well as the total charge matching on both sides. But what if you're asked to balance the same reaction in basic solution? The easiest approach is to start with the balanced reaction in acidic solution and do one extra step to switch it to basic. For this, add hydroxide to both sides of the reaction to match the hydrogen ion in the reaction. In this case, 8 hydroxide ions are added to both sides because of the 8 hydrogen ions on the reactant side. When hydrogen ion and hydroxide ion combine, they yield water. So the 8 hydroxides and 8 hydrogen ions on the reactant side become 8 molecules of water. And this leads to 4 water molecules on the product side canceling out with 4 of the 8 water molecules on the reactant side, leaving us with a balanced reaction in basic solution where there are no longer hydrogen ions in the reaction, but hydroxide ions, as an excess of hydroxide ions would be present in a basic solution and therefore available to be involved in the reaction. So, take some time to appreciate the progression of this reaction from its unbalanced form to being balanced in acidic solution and then balanced in basic solution, and note the differences in the reactions. For a comprehensive list of the steps in the half reaction method, you should refer to this slide, which includes all the steps for balancing in acidic solution, as well as that additional step at the end for balancing in basic solution. This concludes the 7th mini lecture for material from Chapter 8. Please note any questions you may have about this material and how it is utilized to solve problems in the suggested end of chapter exercises and the sapling homework for this chapter. Please post any urgent questions on Piazza. I will also take questions on this material during one of our required class meetings, and during that time, we will focus more on problem solving for concepts in this chapter.